Hello. In this short video, we're going to give you some background information on determinants. Specifically, we're going to show you how to use determinants to help you solve systems of equations, and this method is called Cramer's method. This method will be important to help you understand how the King-Altman method works when we derive rate equations that describe enzyme mechanisms. To begin, we're going to start with two equations, AX plus BY, and we're going to say that equals a constant C. And our second equation is going to be dx plus EY, and that is equal to the constant F. So we have two equations and two unknowns, x and y. Therefore, we can work through quite a bit of algebra and solve for x and solve for y. I'm just going to focus on x, but what I say about x will also apply to y. And to shorten our work and not have to do quite so much algebra, we're going to use Cramer's method. So we're going to say x is equal to, and I'm going to draw something that might look a little strange on the right-hand side of this equation. These parallel lines in the numerator and the denominator are going to be where we write our determinant. Now we form our determinant in the denominator by simply using the coefficients that multiply x and multiply y in our two equations. So a, b, and d, e. Because we want to solve for x, we need to form the determinant in the numerator using the constants that the equations equal, c and f, and using those in place of the coefficients a and d that multiply x. So we're going to replace the a with a c, and we're going to replace the d with an f. And since we're focusing on x, we're going to keep the two coefficients that multiply y the same, b and e. To evaluate these two determinants, we're going to multiply down the diagonal and form the product CE, and we're going to subtract from this product the product we get when we multiply up the diagonal from F to B, FB. And we're going to evaluate the determinant in the denominator in the same manner. So form the product AE and subtract from that product dB. So we can say that x is equal to CE minus FB divided by AE minus dB. Now, why this method works, we're going to do some formal algebra. So we will start with our original two equations, ax plus by is equal to c, and dx plus ey is equal to f. And what I'm going to do is I'm going to rewrite the first equation down here, ax plus by is equal to c, and I'm going to multiply both the left and right hand sides of the second equation by b over e. And I think the reasons I'm doing that will become clear in just a minute. I'm going to rewrite this modified second equation underneath the original first equation. So we have BD over E times X, and we have BY, we have FB over E. So if we look at the original first equation and the modified second equation, we see that we have by in both equations. So if I subtract the second equation from the first equation, I'll get rid of the terms that contain y, and I will have effectively isolated, or I'll be left with the variable x as my only variable to worry about. So we're going to get ax minus b d over e times x, and that is equal to C minus FB over E. What I would like to do now is multiply both the left and right hand sides of the equation by E. When we do this, we get AEx minus B dx, and that's equal to CE minus BF. We have x in the two terms on the left-hand side of this equation, so we can factor x out. So we have x times AE minus BD, and if we divide both sides of the equation by AE minus BD, we will have solved for x, which is what we wanted to do. Now, if you compare the expression for x that we just now obtained with the expression that we obtained using determinants, you will see that the two expressions are equivalent. So this justifies using Kramer's method to solve for x. We could have done the entirely analogous steps and solved for y, but we're going to leave that to you.